work of my whole team. So mostly Martin Kýžanko, Karel Beneš, Oldřich Kodym, but there were multiple other, especially master or bachelor students who worked with us in the last 6 or 7 years. So where I'm coming from, of course, I'm a machine learning scientist, computer vision scientist, but roughly 7 years ago, I was thinking what to do next. And one of the topics which interested me actually was historical documents, because like the old work in even libraries, but mostly, especially archives, looks like this. There are big piles of documents. They read them, take notes, and there was mostly no automation, especially for handwritten documents. In fact, especially these days, the technologies which can process data are so far that we could work much better with the content. We could do things like even have translation, full text search. These days we have chatbots which we can actually talk about some content of documents. But all of this starts with having the content digitized and in machine readable format. So when we started with Project PERO, I really thought, okay, now's the time. We could actually make handwritten text recognition at useful level. Like, it wasn't perfect at that time, but the technology was definitely there. And I thought, okay, if we took big enough neural networks, then we can solve this task, and if we get enough data. Where we are now, I'll show where we are now at this point. So basically, for text which is written well and which is readable, the level of transcription is basically perfect. It can be used for search, it can be used for reading instead of the original text. For example, what I'm showing here is a letter by Václav Havel, which he wrote from prison to his wife. And even though it's not perfect handwriting, the transcription which we have is almost flawless, and it's quite often it's especially me, I can read it better than the original text. We work with libraries and archives, so we work with quite different types of text. This is current, in this case, German, which was used in 1817 up till early 20th century. And basically, we can process this type of documents given enough data, which we actually have. And this allows really applications like translation to Czech language, search in Czech, in these old documents and so on. Sometimes you can go even further. I think this is a document from 1613. It doesn't look like that, but it's probably Czech, or at least some older version of Czech. If I try to read it, it says chorvatský král, arcikníže saský, markrabě moravský, lucemburský, slezský kníže, lužický markrabě, oznamujeme tímto listem všem. The transcription is readable. So this kind of technology really allows normal people to look at and read documents which they couldn't. And of course, we use these tools even with our students. So, for example, here is our test from course on artificial intelligence and machine learning. answer about large language models. And I routinely use our tools to make sense of students' handwriting. And as you can see, we can even read Slovak language. So what do we have? And Project PERO, my aim was, okay, if we want to make some kind of contribution, we have to make our tools fun. So at the beginning, I aimed to create application where people could process their own documents. You can try it. We are running PERO-OCR .fit.viewtbr.cz. Please don't. Today there's a lot of traffic, so if you try it, it may take some time to transcribe the document, but it works. It's an application used by roughly 1,000 people. In the last few years, it processed almost 700,000 pages, and it's also a source of training data. So we have corrected text lines, which we have there roughly 1.5 million text lines in all types of text, printed, handwritten, historical handwriting, and so on. For those of you who work with speech recognition, I would say it's roughly 1,800 hours of equivalent speech. And this is like, it's not some high maintenance system. Basically, we have a virtual machine with 2 cores, 6 gigabytes of RAM, and in my office, I have my old PC with the GTX 1080 and basically my old colleague's PC having Titan X GPU, and this is where we run the whole application. By the way, if you would like to try our software, of course, you can use the web application, but we also have API, where I can basically give you some test API key, and PERO-OCR is such as a Python package. It can be downloaded from GitHub or installed with pip, and you can try it. We have some models available online. So what we actually do, the most basic OCR pipeline has at least 2 stages. It has layout analysis, which the most simple case detects something like paragraphs and text lines. Then in our pipeline, what we do is we crop individual text lines, and then we have OCR network which transcribes these individual lines. So from this point, it's basically exactly the same as speech recognition. So we have
Can anyone hear?
No, I think we lost Michal.
Yeah, I try to call him.
Yes, please, if you can.
Yeah.
Yeah. Perfect. So sorry about the interruption. So really from after we get the layout, text, and the text lines are extracted, then it's really similar to speech recognition. And in what we do, I really try to make the results usable, so we have a reasonably well working web application where users can work with the results, can correct the results, export them, and so on.
I think we lost him again.
Yeah.
Michal, can you hear us?
I'm calling him.
Maybe, I don't know if in either Honzo or Pavel Zemčík, if you are close, maybe he can use, your connection.
Yeah, he can move to my office basically. I'm at home, but if he is in the meeting room, I think he is. My office is 2 meters.
I'm actually next door and I have it running, so I'll invite him here. Let me talk to him. Okay?
So
is Misha in L? Okay, Misha, we again lost you. Maybe are you in L220?
okay. So layout recognition. Okay, it's not that simple. Especially with handwritten documents, it sometimes tends to be really problematic. Like in this case, I don't even know what actually the layout should be. Okay. So sometimes it really is not that simple. Sorry, few technical. Don't go there. Okay, so basically this is what we do. These days I would be thinking about using some object detectors like YOLO version 8 or something like that. But when we started, we actually started with something which would be quite flexible and which could actually handle any shape of text lines and so on. So basically, we handle layout analysis as segmentation. So we have image, run it to sort of like UNet or any other segmentation network. Originally, we had some specifically designed multi-resolution network detecting basically segmenting baselines of text. And on top of that, we have simple post-processing, just taking connected components, building text lines from that. Actually, we started with this and during the years, all of it just became more simple, and now we have completely standard, very fast and robust segmentation model here. So detection of text lines and regions is not the end. Like when people want to read a document, they actually like to have nice reading order. This is something which we were struggling for the whole time we have the application. This is some older result from our system, and it's definitely not perfect. It's you can see the line basically represents the reading order. It doesn't make much sense. It doesn't work for all the layouts and so on. Basically, it's because it's hand-coded, hard-coded there by one of my students. This reading order should definitely be learned, but we've tried few things, and we couldn't get anything really to be robust and work most of the time. What we actually did last year is to at least try to get not a global reading order, but to segment documents into meaningful parts. So things like articles in newspapers or single keys in slovníky and so on. We have a software which is called TextByte, and it's fairly simple. It basically uses object detectors, so it detects regions which are definitely belong together, and then it has a graph neural network on top of that using text embeddings and geometric positions, and it is able to merge connected parts of the text together. and it will be published in 2 days as a diploma thesis by my student, hopefully coming to have PhD here. So that's the layout, fairly simply. And on top of that, and where most of my work actually is focused is the text recognition. So we have 2 versions of models. One is based on CTC loss. CTC loss is basically loss which can take some input text, in this case text line, extract features from that, extract logits. Thanks. It extracts logits every, let's say, 5 pixels. It gives these logits predict characters. And when we have transcription of the text line, CTC loss basically uses dynamic programming to align those logits with those transcriptions. It's fairly simple, and these models in our case are like, here is a simple version, standard convolutional network ending with sequential layers. In our case, in our production models, it's actually LSTM layers in multiple resolutions. So like having node every 4 pixels, every 8 pixels, every 16 pixels. So this type of multi-resolution LSTM layers and CTC on top of it. Of course, these days, we are transferring to transformers. These models are exactly the same. If you've read Whisper or any other speech recognition and transcription models, it's the same. It's a model which takes text line as an input, has some very simple convolution layers. We are using still BGG as part of BGG networks, which extract a sequence of features, run through encoder with positional embeddings, decoder predicts tokens, and we are generating text. We had hard time making these models better than our old ones because the CTC models were really fine-tuned, really working well. And it took maybe 2 years to actually make these transformers perform better than CTC models. And most of our research, which I'll show right now, is actually with those CTC models. In some of the applications, most of them are actually come from running our applications. So we always have, okay, we have this type of data, we have this application, we need our models to work better for our users. So what should we do? So one of the problems which we had from the start is that each user, in our case, wants to have different transcriptions. So we have single text line, and depending who the user is, if it's a linguist, historian, librarian, they want different transcriptions. And when we collect transcriptions, they have these different styles. And each person wants a different style. So what we basically did, we created a fairly simple network where we just included adaptive layer, which basically uses embedding of a user. This embedding should encode the transcription style preferred by the user. And during runtime, this embedding basically changes the output of the network. Yeah, so really, I can get different transcription from the same model than someone else. And this basically helps us a lot when we have a big data set of transcriptions by our users. And we don't look at those transcriptions, we just learn the embedding for each user, and the model works well on this weird data. One of the most useful thing is really to have something like active learning workflow. When we are running the application, basically images get uploaded into the system, processed by our existing models. The user has fairly usable user interface, where the main part is that we don't show just the transcriptions, but we have fairly well calibrated confidences, and we basically highlight those characters where the model could make errors. Users can go fix that. We collect the data and we let the users transcribe the document again. In this case, actually estimate the transcription style preferred by the user and transcribe it again. We tried the same thing with writing style adaptation. So basically, my idea was, okay, we want to have a model which can, be fairly small, but it can change how it works for different users. So basically, based on how they write, not how it should be transcribed, but how they write. And we tried the same thing. We tried to learn basically embeddings for each document, and then change the behavior of the network for each document by including adaptive normalization in the models. This sort of works, but we don't use it in the system. It's not that practical, and the gains were fairly small. So I would like to have models which can adapt to different input data, change their behavior, but it doesn't work much. The gains are small. What actually works extremely well for most of our cases is domain adaptation. So just simple fine-tuning. What we did, and we can't basically beat, is just have a big model trained on a lot of data, and then collect few text lines for specific user for specific documents. And we get these types of reductions in error rates. So basically, each line in this graph represents different document. And for example, for some of the documents, we can get like 50% error reduction with just 8 text lines corrected by user. So we let users correct few text lines, they transcribe the document again, and they get twice better results. And it's really just simple fine-tuning. But we struggle to make this work actually with transformers. It works with great with CTC, but not as great with transformers. And basically, we have this type, this type of automated loop whenever user corrects some errors in a document and transcribe the document again, the model is first fine-tuned to actually that document. And because basically label data is expensive, we tried also different approaches to use unlabeled data. One very simple approach is self-training. Basically, it just says, okay, if I have a model, I run it on new data which don't have labels. Then filter the text lines with highest confidences and train the model on that. So basically train on generated labels. If this is done correctly and carefully, this improves results. But again, like the improvements, it's hard to make the improvements significant and consistent. So this works sort of in the lab. We have a paper on that, but it's not used in the system because it's too much work for too little gains. What we also tried to do is, I am actually quite proud of this work by Martin Kiš. He actually took the CTC loss and made it work for soft labels. So for labels where the transcription is not just one transcription, but we have sort of different ground truths with different probabilities, confidences. And basically we have implementation of this soft CTC loss, which can take like infinite number of variations of transcriptions and train all of them with similar runtime efficiency as normal CTC loss. But again, for self-training, this doesn't help much. Then, of course, how to use a lot of unlabeled data is by self-supervised pre-training. We have a paper this year, again by Martin Kiš and myself, basically looking at different methods, self-supervised pre-training methods for text recognition. We tried things like AICZECHIA and different masking predictions with transformers. Basically, the point is these approaches work. But again, there's the very strong baseline, which is just the domain adaptation fine-tuning. And in the future, like we want to try some large-scale experiments with a really lot of unlabeled data. But in the smaller scale experiments, fine-tuning is always better than this type of self-supervised pre-training methods. And right now, what we are working on is really just to make transformers work really well. Right now, they are our best models, but there's still room to make them better. And it's interesting that there are sometimes really simple things. For example, with transformers, when we use positional embedding, standard cosine sine positional embedding, one aspect is, okay, these models will not learn to generalize to different lengths of encoder or decoder. So just in our case, just simply shifting embeddings in the temporal direction actually makes these models from okay, working somehow, to working really well and making them really the best models which we have. And we have actually quite several open questions with transformers, which we are working on right now. One is, okay, can we make fine-tuning work really well with transformers? So how to make transformer model, how could we adapt a big transformer model on, let's say, 16 text lines, which is something like maybe 1 minute of audio. So, I'm not sure how to do that. Honza Code has some good ideas. We'll see where it goes. And there are questions like, right now we are usually transcribing each text line independently, but context should help. So how to use context, either images or text, to improve the results, feed them in the model. I want to try experiments with translation. So something like Whisper, learning these OCR models, not just to transcribe documents, but also to translate them. So the question is, will it help? Will it improve the models? And what I actually feel like it's simple and should help a lot is to feed some keywords. So text which is not used too often, but it's used often in single document. To give it to the model during transcription to guide the model, basically tell the model, okay, this document contains this set of characters. If you see something like that, transcribe it that way. That should be fairly simple and should improve the results. And of course, I want to have really large-scale self-supervised pre-training for the models, and then train, especially for encoders, and then train the full model after this self-supervised pre-training. We'll see how much data and how big the models will have to be to make this actually useful. And of course, right now we are working most of the time really on making this slide work, really basically on using these transcriptions to create actually useful applications for users where they could actually find information documents, analyze the information, translate it, and so on. And we'll see where it goes. Thanks.